All right, so let's see what we are going to do today. So we got started with a little bit of concept learning task in the last class, and today I'm going to do a quick recap. I also realized that I was throwing a lot of confusing terms at you, so let us first try to get those things sorted out, and then we can move on to other algorithms as well. All right. So what we did in on Wednesday was introduce this notion of concept learning. But before that, we defined some terms. We defined a data object. We said a data object or an instance is defined using D attributes. To make our life easier, we said all of these D attributes are binary, which means that if you have D attributes, then you could have 2 power D different objects, right? That's clear. I made a little demonstration for you. So we were looking at this example of looking at brain tumors and trying to classify them into different categories, right? So let's say these are all our brain tumors, and I have, instead of the picture, I have written their attributes here, right? So if you look at it, see, now here we are assuming that D is 3. There are only 3 attributes. One is the size, one is the color, and one is sort of the surface. And all of them are binary, which means that you can have 2 power 3 or 8 possible types of data objects, right? So this is your world. This is your world of objects, and we denoted this with the symbol X. And then we said, okay, there could be 2 power D, which means that X is 2 power D. But this is only true if all of these are binary, right? The second thing we introduced was, so this is our data. The next thing we talked about is a concept. Now, concept is a little hard to define, but you can think of, so there are 2 definitions. One is a mathematical definition, which we will work with. But in general, in a semantic sense, a concept is something that, tells you something about objects, right? So, for example, we were looking at this example of students. So, one of the concepts would be to know if a student is undergraduate or not, right? So, the notion of a student being an undergraduate is a concept that we want to learn. You could have another concept for the same data. So you could have a concept which says, is this student a computer science major or not, right? So, but that's a different concept which is applied to the same data set, right? So you could have many concepts like that. In the case of tumors, one possible concept is this concept malignant or not, right? Another concept could be, is this tumor malignant or not? Another could be, is this tumor, on the periphery on the tissue? Is that a tissue tumor, or is it on the cerebrum or other part of the brain, right? So I'm not an expert in this, but there could be different semantic concepts that you might want to learn, right? But what every concept does is that it divides your data set into 2 parts. One which belongs to the concept, and so one part which belongs to the concept and one part that does not belong to the concept, right? So then we introduce several terms. So we can say that a concept agrees with a data point X which belongs to X. If X, that's the semantic notion, belongs to the concept. That means that, so if your concept is malignant or not, then if X is malignant, then this agrees with the concept, otherwise it disagrees, right? Sometimes we also use the terminology accepts. A concept will accept a data object if it belongs to that, right? Mathematically, we said that we can treat the concept as a function. Mathematically, we represent the concept with the symbol C, and it's actually a function which takes in X and it produces an output, right? The output could be +1 or -1, which means +1 means it accepts the X or agrees with X. It could be 1 or 0. It could be true or false. So there are many different notations there, and unfortunately, even in my notes, I sort of go I switch from one to another. So, but slowly, I think I'll make it more consistent. But whenever you see any of these things, it essentially means the same thing, right? So, mathematically, concept is a function. What the concept does is it essentially divides your data set into two parts, right? And so then we said, okay, how many ways can you do that? So you can divide a set of D objects. Here there are 8. In how many ways? 2 raised to D, right? It's a combinatorial thing. So you can either put them. So there could be a concept which says all of them are, it accepts all of them and rejects any nothing. There could be one which which calls nothing as positive or nothing as accepting. That's another one. There could be one which calls one of them as positive and everything else as negative. Now, how many ways can you choose that one of them is 8 ways because there are 8 of them. So that's 8 possibilities and so on. So you just do and choose 1 and choose 2 and choose 3. Go all the way to and choose n, and that is 2 power n. To size of how many ever objects there are here. So that means that possible number of concepts is 2 power size of x, and if x is defined using binary attributes, then this becomes 2 power d, right? So it's a pretty large set. Okay, so the task of concept learning. So now, so there's a concept, right? So let's say our concept is malignant or not. So essentially, what will happen is that a force of nature is going to label these at the back. Let's call this malignant, 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 and rest of them as benign or not malignant. Benign, 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 right? So that's what your data is. Now in the learning task, what happens is that you will be given a training data set, which is a subset of this. So it will give you maybe 1, 2, and 3. For these data points, you know what their attributes are, and you also know what their features are on the other side, right? So that's your training data, and your job is to learn that C, so that if now I give you one more, then without looking at what is in the back, you can tell me if it is benign or malignant, right? Very easy. So, so that's the task of concept learning. Now, mathematically, it essentially means that there is this space of concepts. I'm going to make a fancy C, and the size of C of fancy C is 2 power d. And you have to find that target concept, the one that labels these things, okay? It lies somewhere here. You don't know where it lies, right? Now, since the size of this C is very large, it becomes a very challenging task. In fact, it becomes almost impossible task to search for concepts if I give you a partially labeled data set. So what we essentially do is we make simplifying assumptions on the type of concepts that or we make a simplifying assumption on the concept. We say, even though we don't know the concept, we can make an assumption that this concept will have this form, okay? Which essentially the effect it has is it narrows down your search space, and then you have to search in that space, all right? And that's kind of the crux of any machine learning algorithm. It's very hard to search for all, it's very hard to search in the entire space of right answers. So you constrain your space and then look for the answer there. One thing that could happen is that maybe your answer is not in this set at all, which means that you made a wrong assumption, and then you're doomed. You're saying you can't do anything. But in those settings, you hope that the answer that you get is still useful, right? But we will come to that later. Today we are going to, at least for this week, we are going to assume, yes, my concept does lie in this space, and then how do I find it there, right? So one assumption we made is this notion of conjunctive concepts. So conjunctive concepts are those concepts that of course belong in this big set, but they have a special type, which means that they can be expressed as a conjunction of one or more attributes, okay? So you have the attributes, So you can, the restriction that you're imposing on these concepts is that these need to be expressed as a conjunction of something. So it could either be small and dark, or small and dark and something, right? So it needs to be of that form. And then we did this calculation in the last class that if you have binary attributes and you are trying to find conjunctive concepts, then you can have three, that the possible conjunctive concepts will be 3 power d plus 1. Okay? Because if you look at it, essentially what a conjunctive concept would look like is that you have your d attributes. You can either have that attribute in the conjunction or you can have its other form. So it could be small or large, dark or light. So, or you can ignore it, right? So there are three possibilities, and for each one there are three possibilities, and so on. Right? And then there is one special concept which cannot be expressed with this, which is in which you reject everything. No matter, you don't even see what the attributes are, attribute values are. You just call it not malignant, right? So that's, we usually represent it as a phi or all phis. It doesn't matter, right? So this is called a reject all. So which means that total it will be 3 power d plus 1. All right. Any questions with that? All right. Good. So as I told you earlier, right? So we have done this. That force of nature had done this labeling for you, which meant that it called these 5 tumors as malignant, sorry, as benign, and only 3 as malignant. But it's not necessary that the concept that defines this will be a conjunctive concept, and we can look at it, right? Look at this: large, light, smooth; large, dark, irregular; small, dark, smooth. So actually, you cannot come up with a non-trivial conjunctive concept to define this. So, but and that is the point, right? So you could have any concept that sort of divides these into two sets or colors them in two colors, but only some of them will be conjunctive. Some of them can be expressed as a conjunction. A lot of them will not. Okay. So with that assumption, what we have done is we have made our life very simple. And now we looked at one algorithm. It was called find S, which can find your, or which can work on this data and try to move towards your target concept. Okay. So another term I want to introduce is that now whenever you have an algorithm which is trying to learn this concept, since it doesn't know the concept, we will use this notation of a hypothesis. So a hypothesis is what it means. It's a guess, right? So it's a guess for what the right concept is going to be. So usually we use letter H to denote it. So essentially what these algorithms will do is they will sort of try to learn, they will start with some hypothesis and they will refine it as they see the data. And at the end of it, whatever they get, once the data is exhausted, they say, okay, I think this is the target concept. It may or may not be. So that's why we call it a hypothesis. All right. So let's quickly review our algorithm again. That was our find S algorithm. I found out why they call it find S is because it tries to find the most specific concept based on the data. Where is that? We saw all of that. Right. So this is our find S algorithm. So the idea is pretty simple. You start with the most specific hypothesis, which is call everything not malignant, right? It's a fair way to start. Then as you see the data, as you see your training data, so x comma cx is the training data that you get. Basically, it's this card. You get one card. If it is benign or if it is not the target concept that you are trying to learn, you discard it. But if it is malignant or if it is 1, then you do this business. You refine your hypothesis. Okay. So in the beginning, your hypothesis will reject everything. In the next step, your hypothesis will get refined. So this refinement is basically a pairwise AND, but of course it's a special pairwise AND. So it goes by these rules. All right. And I told you last time that essentially it's sort of using common sense, right? So in the beginning, you say, I don't think anything is malignant. Once you see the first malignant item, you say anything that looks exactly like this malignant item is going to be malignant, right? Next time you see another malignant, you do a bitwise or pairwise and then you get a refined hypothesis and so on. So basically, you will be step by step. You would discard all the unnecessary attributes, and you'll be hopefully you'll end up with what you want. Right? Any questions about this algorithm? I will set a problem in gradients which makes you work this out on some data set. So that will make it easier to understand. All right. So let's look at a simple example. Let's say your target concept is this. It's large and thick. That's how thick. So the way that works is that force of nature will look at your, so large and thick, let's remember that. So this is our example. Our target concept is large and thick. I mean, technically you want to write all the attributes and replace them with question marks if they are not being used. But here I'm just using, let me write it like that. Question mark large, question mark thick. So essentially what that means is that whatever the force of nature is, it's going to look at these and, oh, this is different. But, if it is large and thick, then it's going to mark it as malignant. Otherwise, it's going to mark it as benign. So that's how the data was generated, right? Now you want to learn this. So the first question is, how many positive examples can there be if this is the target concept? Right. So how many of these 5 attribute tumors will be labeled as positive or malignant by this? 2? 2 is not right. There are 2 here. I'm sorry. There's a question mark and a question mark. So anything which has large and thick, but these can be anything, right? So it can be 2 times 2 times 2. That's 8. So you can have 8 positive attributes by this concept, and everything else will be negative, right? That's just a simple sort of combinatorial thing. Now the next thing is that how many training examples you need to see so that your find S algorithm learns this, right? That's the next question. So how many training examples do we need? So the answer to this is that, of course, it doesn't matter how many negative examples you take because the algorithm ignores them, right? If you remember the algorithm, it doesn't look at negative training examples at all. So it could be all of the training examples. So in this case, there are 8 of, so there will be 24. So yeah, 24 negative examples, right? So in your training data set, you could have all of those 24 examples. The algorithm would still give you the same answer. Go ahead.
I thought you said that start with the find S algorithm, the all null values.
Right.
So then how does this target concept get formed?
Oh, yeah, good question. So this is actually not the concept that the find S has learned. This is the true concept that you want to learn. This is the concept that has divided your tumors into 2 parts. See what I mean? So this is not available training algorithm, right? However, since this concept generated this data, so we know that it will be divided into a set of 8 and 24. I'm right? Would it be 24 negative examples? Yes. All right. So one thing we note is that number of negative training examples do not matter. does not matter. The number does not matter, right? Because it does not look at those examples anyway. But now it comes to how many positive examples you need, right? The answer is that you don't know. You could actually learn this with maybe two positive examples, and that's it. Because let's say your first positive example was this: circular, large, light, smooth, and thick. So that's positive. That means it's malignant. And the second one is oval, large, dark, irregular, and thick. All right. Now remember, this is our target that you want to. So what will happen is in the first step, your hypothesis will be this, right? And in the second one, you will do a pairwise or and with this. So you will mark the question mark, this will be question mark, and this will be thick. And then this is this, right? Now after this, it won't change. Even if you had more training data, your hypothesis will not, because any negative example that you get after this, that will be tossed out anyway. But if you get a positive example now, those positive examples would have large and thick, right? Because that's what generated this data. So you would be doing a pairwise, and anyway, all of these would not matter because the pairwise and ignores these couples, right? So that means that you might, if you are lucky and your training data has only these two attributes or these two data objects, you would still be able to learn the target concept, right? So what you see in this find F algorithm is it depends on what training data you get. And it also could happen that your training data is bad and you might not learn this at all, right? So there is no way to find that out. The order also matters, right? So for example, let's say before this you had bunch of other examples, you might eventually learn this, but not in the first two examples. So it matters what the order is, it matters what your training data is, right? So that's kind of a little bit analysis of this algorithm. Any questions so far? Yes, go ahead. Yes. Yes, so that's a very good question. The follow up on that? Oh, okay. Yeah, so the question is that what if there is some mistakes in your data, right? It's assuming that your training data is. Right. Exactly. To fail. Yeah. Yeah. Right. It's always right. Yes. Yes. So that's a good question. So the question is that, what if, but remember that we have made this very strong assumption that your target concept is conjunctive, which means that if it is thick, it has to be thick if it has to be a malignant one. But that's not a very practical assumption. So the point being, I'm glad you raised this, is that this is not a practical algorithm at all. This is actually the worst algorithm. So don't go for your job interviews and say, hey, I apply find S to your problem, because this makes too many assumptions which would not hold in real settings. And also related to that is that if your training data has some errors, let's say somebody by mistake, instead of writing small wrote large, then this algorithm can get really messy. I mean, it can just go away in some other direction, right? So it's not a very practical algorithm, and that's a good point. I agree. So the reason we are looking at these algorithms is more for just to analyze them, but we will see those kind of algorithms maybe 2 weeks later, in which case, says one attribute is useful in most of the times, you still want to use it in practical settings. So we will look at them later on. But for these algorithms, we are making this strong assumption that your target concept is conjunctive all the time, right? So keep that in mind, of course. Any other questions? Yes. Right. Yes. So we are assuming that there is no errors in the data, in the sense the labels are also correct, and your features are also attribute values are also correct. That's true. All right. So moving on. So that's a good point, and what that essentially tells you is that this is a very useless algorithm in some sense, right? It's good to do some analysis, of course. So now what we're going to do is try to see what happens if you have only some of the data. You don't. So let's look at this example again, right? Let's say again our target concept is still the same, but we get this as our training data, right? So when you go home, you can work this out, but essentially you need to pass it through the finders algorithm. What the finders algorithm will do is eventually it will learn this concept, okay? Because it's very easy to work out, right? So you just take the malignant ones and you just choose the ones that are true always. So large will stay, light will stay, and thick will stay, right? Of Any questions? All right. So and of course, this is not the target concept, but this is where it will stop because this algorithm doesn't know anything else. Once it exhausts the training data, it has to stop, right? But now let's see, can this in real setting, will this algorithm, will this concept that it has learned make any mistakes, right? So do you think it will make any mistakes? Right. So it good. So false positive, which means that it is going to call something which is large, light, and thick as a malignant tumor. However, a large no, you get a false. Yeah. So it's going to call a large, dark, and thick as not malignant, right? Because it's going to reject it. If you by this conjunction, it's going to call large, dark, and thick as not malignant. However, large, dark, and thick actually is malignant because in reality, only large and thick matter. Doesn't matter what color it is, right? So, but the reason it is making mistake is because it has only looked at partial data, right? So this is another point that finders algorithm only gives you partial result, right? One thing you can take away is that it will never make a false part. It will never call something benign when it is actually malignant. Is that right? I need more coffee. It will never call something malignant when it is actually benign, right? It will never call anything malignant when something is benign. Why? Because if it is benign, then one of these has to be false in that example, right? That's because it's benign, right? So which means that when you do the or, it will call it negative. So let me expound on that a little more. So let's say partial concept learned by is mark 6. All right. The time is. All right. So my claim is that even with this partial concept, it will never make one type of mistake. Will never call a, a benign there's the other way, right? It will never call a malignant tumor benign. Is that right? The other way, huh? I'm sorry. I should have practiced more. Uh, it will never call a benign tumor malignant. It will never call a benign tumor malignant. For example, of course, we saw that it could call a tumor which is question mark large, question mark large, dark, question mark thick as benign, even though it is malignant. So it can call malignant things benign. Right, you're right, you're right. Call a benign tumor malignant. I mean, it will never call a benign tumor malignant, right? And I want you to go back and sort of think about this. It's easy to see. Basically, the idea is that whenever there is a benign tumor, of course, you don't know its label, but what you know about a benign tumor is that it would be large and it would be thick because that is the process that generated that label, right? So because it was large and thick, it was generated as malignant, which means that if it is a benign tumor, either it won't be large or it won't be thick, right? And that's true when you do a pairwise AND of that coming object with this, it would yield, it will always call it benign. So it will always call benign things benign. It might call a malignant thing benign as well, which is the issue with the finder's algorithm, but not the other way, right? Okay. In last two classes, actually, last 2 years, I used to have a homework based on this, but this time I'm going to introduce it into gradient, so you'll know more about this. Any questions so far? All right, fantastic. Anyway, so what we have concluded by spending so much time is that this is a completely useless algorithm, which means that we need to look at something better. All right. So let's see. Okay. So we are going to look at an algorithm which can do a little better than find S. All right. It would still work under the same assumptions that your target concept is conjunctive all the time and your data is binary and everything, but it will do a little different thing, right? So to do that, we will first introduce the notion of version spaces. Okay. So what is a version space? Version space is associated with a training data set. Okay. Once you have seen some training data, all right, there could be many hypotheses which are consistent with the training data. So what is consistency? Consistency means that it will call any malignant object malignant and any benign object benign. Okay. In the training data, not in general, right? So for example, let's say this is our training data that you've seen. The find S algorithm found this, right? Now this uh, hypothesis is consistent with this training data. Why? Because it will, if you had hidden this malignant label and if you had done a pairwise AND with this, it would call it malignant and it would call any benign object as benign. So this hypothesis is consistent with the training data. And what find S guarantees is that it will always produce a hypothesis which is guaranteed, which is consistent with the training data, because that's how it works, right? But what it turns out is there could be other hypotheses as well, which would be consistent with this training data. All right. But since find S kind of searches in one direction, so it only gets to one, but there could be others as well, right? So there's all these hypotheses which are consistent right now with this training data. We call them a version space. It is a set of all consistent hypotheses. All right. So now instead of learning, since you only have partial training data, right? So what we have understood is that with partial training data, we might not be able to reach the target concept, right? But what if we come up with an algorithm which can at least produce the version space, which means that your concept is guaranteed to be in the version space, right? Because version space, so version space, as I said, is set of all consistent hypotheses with D, right? Because the consistency is measured with respect to your training data, right? Which means that let's say this is your fancy C, this is your conjunctive space, then version space is somewhere here. This is your VS, right? And your C is guaranteed to be inside this version space because that also will be because your C will also be consistent with your training data, right? C will actually be consistent with all of your data, but you don't know that, right? So now we will look at an algorithm which can help you find the version space at least, right? So that you at least know that your C is in there. So it's a little more guarantee, right? Whereas with what the finders algorithm does is it finds a C prime, which would also be in the version space, of course, but it would just be one. It might not be C, so it might be far away from C, right? So that's the issue with things. So now let's look at one algorithm which does that, and we call it very imaginatively named list then eliminate. Okay, so what this algorithm does is it does the reverse, right? Remember, find s starts with one most specific hypothesis and then it iteratively refines it. What this one does is it says that my version space is actually my entire hypothesis space or the entire space of concepts. So you can call it the conjunctive concept space or the hypothesis space, right? So we start with that, and then as you see more and more data, you start removing the hypotheses which do not belong to which are not consistent with the data so far. Okay, so first you start. So list then eliminate. What this does is starts with H. Now H is essentially this, okay? Whatever your conjunctive or concept space is right now. So starts it. So it says that VS is H, which means it has all the hypotheses. Since you have not seen any training data at all, which means that all hypotheses are consistent with this, with the empty set, right? But now you get the first training example, you remove, after you get the first training example, remove all H that are inconsistent with your training data. So right now your D is only this, right? Then you get another training example. Now you remove all the hypotheses which are inconsistent with the training data so far, and so on, right? So what this does is, this algorithm, it guarantees that at any given time, once you have exhausted all your training data, what you have is the version space. Okay, that's pretty clear, right? That's how it works, so it has to find the version space. However, and then there are some, if you look at the notes, I have some notes about some issues with this algorithm. Mainly, it's a computationally very expensive algorithm because at every point you have to explore the entire versions or entire hypothesis space. So remember, when you start with this fancy H, the size of this H, if it's the conjunctive concept class, is 3 power D plus 1, right? So if your D is pretty big, even if your D is 5, then 3 power D plus 1 is 244, I think. So you have to scan through all of them and see if all of the training data are consistent with this, and then you remove the ones that are not. So it's very computationally expensive, right? So then comes the next algorithm, which lets you find the version space in a more computationally efficient manner. Okay, we call that algorithm candidate elimination, and it comes a little later. Let me see the time. Any questions so far? Yes, go ahead. Yeah. Right, but if you think about the version space algorithm, is that it starts with the most specific hypothesis, but every time it is outputting only hypothesis as the output, right? So it's kind of moving in that space and trying to reach. So what this, so let's say this is our concept space. This is the bigger space, of course. Your target concept is here. What list then eliminate does is that it starts with the most specific hypothesis, which is somewhere, and then slowly tries to move. I mean, this is just pictorial. There's no direction, but it tries to reach here. But it might not, because you might not have the right training data. What list and eliminate does is it starts with this as your version space, and then it tries to sort of narrow it down, make it smaller and smaller and smaller. And what it guarantees is that when you have exhausted your training data, whatever version space you're left with will contain your space, right? So it's a little better algorithm in that sense, because it guarantees, it provides you some guarantees, right? The versions find as algorithm doesn't provide you any guarantee that how close is this to the real, to the correct answer. So that is the difference. So that's a good question. All right. So to understand this next algorithm, which is called candidate elimination, we need to understand something called compressing this version space. So it turns out that this version space, right? So version space is just a set of all your hypotheses. It turns out that you can arrange your version space in sort of a hierarchy. All right. So you can, if you look at all the consistent hypotheses, you will see some of them are very general, some of them are very specific. So you can arrange them in a certain order. So let me go back here. Right. So for example, we have seen this example before, right? So if this is your training data, you will see that all of these hypotheses are consistent with this training data. So this is essentially your version space right now. There might be more as well, but at least these are part of your version space, right? So what this notion of compressing version space says is that you can arrange these hypotheses in this order such that you can say that one hypothesis is more general than another. So there are these definitions called, there's a relationship that we are going to define, which is more general than relationship, which means that one hypothesis is more general than another if whatever objects one hypothesis accepts, the other one will also accept. So in simple terms, so more general than relationship, right? So let's say you have a hypothesis called, example, question mark, large, light, question mark, thick. And let's say you have another hypothesis, question mark, question mark, question mark, large, question mark, thick. All right. So we say that this hypothesis is more general than this one. Why? Because it will act, whatever objects this is going to call as positive, or whichever tumors this is going to accept, this is also going to accept, and this is going to accept some more, right? So this is more general. And the same way, there's a definition of more specific, which means that one algorithm, one hypothesis is more specific than other if, you know, it has, basically it's more, it has more attributes inside it, right? That's a very, very easy way to understand it, but mathematically you can write it like this. Something is, there's a more specific than relationship as well, right? And then there's also a strictly more general than relationship, which means that the other one has to have at least one more, right? So that's there, okay? So what this helps us do is it helps us arrange the version space in a way such that there is something called the maximally general hypothesis and maximally specific hypothesis, which means that if you look at your version space, you can identify a few hypotheses such that you cannot go more general than that in your version space, and there will be some which means that you cannot go more specific than that. So those are called the most general and most specific boundaries of your version space. All right. So now what we will do in the next class is we'll look at a theorem and we'll look at the examples as well, which says that if you know your boundaries, then you don't need to know anything in between, which means that now your version space is represented in a much more compressed way. And then we will look at an algorithm which lets you learn those boundaries. Because once we know those boundaries, then by this theorem that we will look at next time, we know the entire version space. Okay, so that algorithm is called candidate elimination, and we'll do that on Monday. Any questions so far? Yes. I'm sorry, I didn't hear you. Yes, yes, yes. Right, exactly. So you're ordering your version space in certain way, and then what that theorem will tell you is that if you are able to learn the top and bottom boundary, then you don't need anything in between, and that's how it will become more efficient. All right, thank you very much. Have a good weekend. Bye.